Hello everybody. Today we are going to take the theory and do some design problems, or what I like, or well, what my professor likes to call a design problem. Basically, we're going to take what we know about phasors, and we are going to figure out what kind of components we can put in a system or network that will increase or decrease the power factor. So last video we looked at the power factor in power, and so we want to see if there are ways where when we're given a network we can actually determine what our power drawn from this network will be. And so here are a few steps that I think are holistic, and will cover everything. So the first step is to actually find the current power and the current power factor of the circuit. The second thing is to graph them. So graph the vector that is produced by the impedance, okay? Because we know that the impedance is related to the power factor. We're going to identify a new angle, phi prime, okay? Phi prime, and this phi prime is going to be the phi of our modified impedance, okay? And then we're going to use the graph to see how much you need to take off, and I added this step because it's nice to visually see what needs to get removed. And then finally, we're going to determine the component, and we're going to look at that more in detail. So this is what the first problem looks like. There's going to be two parts, part A and part B. Let's focus on part A. So step one is find power and power factor. I've just gone ahead and divided this problem such that A will just be all of step one. And we already know how to do all of this. So when we're solving A, there's actually steps within that, within step one, and that's simply to convert everything to phasor. Now the cool thing is that technically, because we're working with P average, or we are going to, we don't need the sinusoidal component. We just need the max amplitude, because we remember that our power equations are 1/2 Vm Im, and then the power factor, and then you can get some kind of we're going to be actually using the one with the v squared more than this one. So step one is to convert to phasor. And because we already know how to do this, I'm just going to go ahead and speed it up right here, but I'm going to show you all the work as normal. So these are now the phasor representation, or within the frequency domain versions of the capacitor. So the capacitor is negative J 8/5, and the inductor is J20. Okay. Now, if you don't know where I got all of this, I would highly recommend that you check out my previous video on my previous videos in this unit on how to convert to the frequency domain, or the phasor form. Now we are going to find the because these guys are in parallel right here, we're going to put them in parallel, and we are left with negative J 40/23. And then we are going to have to actually find the total impedance, which is just the addition between the resistor and this configuration right here, because they're in series. And our Z total will be 4 minus J 40/23. Now that we have Z total, it would be beneficial if we just went ahead and calculated the magnitude. And that turns out to be approximately 4.36. And then, of course, the phi, which turns out to be negative 23.49 degrees, and that will be in quadrant 4. And actually, it would be good to do step 2 while we are doing step 1, so that we can visualize what's going on here. So we can see, and I'm going to exaggerate the angle, but we can see that we have a more capacitive, a more capacitive circuit, right? So I'm going to do this in blue, like this. Then I'm going to label this guy as about negative 23 degrees. And then now we can plug in to find the power factor and the power. So the power factor, if we remember, is just going to be this real part over the magnitude, okay, because it's the ratio, because it's just cosine phi, which is equal to, you can either do 4 over 4.36, or you can do cosine negative 23.49 degrees, and it should all give you the same thing, which is 0.917. And now that we have the power factor, we can find the power average by using our formula. This time we're going to use the voltage version, the Vm squared one, with the power factor on top right here and the magnitude down bottom. And plugging everything in, we get about 1.68 watts. And that's the first part. Now, the second part is the design question part. So the question is asking us to add a component that can be added in series with the configuration such that the power factor becomes 0.95. So that means this configuration right here that we just found the power factor of, and then some component that will go right here. I'll just make a box that will make this power factor 0.95. So we'll move on to step 2, right? Continue step 2 so that we can visualize this. So basically, actually no, step 3. So we've already graphed our Z right here. We're going to do step 3, which is I actually identify this new phi. We can identify it by saying that cosine phi pi, actually p dot power factor prime is equal to cosine phi prime, which is equal to 0.95, right? Because we want this new power factor to be this. And if we take the arc cosine of 0.95, we are going to get 18.19 degrees. But remember, we are more capacitive, so, and cosine's an even function, so we can go ahead and stick our negative sign out here, because when we do cosine negative 18.19 degrees, we should get 0.95 back out, okay? And this is where step 3 comes in handy, and why we drew the graph in the first place in step 2. That's because we can clearly see that our angle is much smaller now. It is negative, what did I say? 18.19. And now it becomes a geometry question. So basically, we want to find a component such that this portion right here, x, is going to be removed from the total, which is y, right? And this total y is actually just simply the imaginary portion of the z total, this, okay? And because we're already down under, I'm just going to say the magnitude, which is j 40 over 23. And so we want to find this, right? Well, we want to find this. So we are actually going to use a tangent. Why? Because we have the relationship where if you add this x to this negative y, we're going to get this part right here. And yeah, and this is the part that we can relate to this degree right here. And so we are going to say that tangent phi prime is equal to O, right? OA, SOHCAHTOA, right, from our high school days, the opposite divided by the adjacent. And we know that the adjacent is just the real part, because this resistor doesn't really get messed up by going up and down. That's the cool thing about phase, is that it's like based on this imaginary portion, right? Or, well, not the phase, but the imaginary portion is the thing that's doing the moving, right? The real part is just fixed, right, at this point. So the bottom is the real part, right? That's just going to stay real. And now the top part is actually going to be y. And if you want to make it negative, I'm just going to say it's y, because I already know that it's negative. So I'm going to say y plus x, right? So that we can get the portion right here that describes the relationship of tangent, okay? And I'm going to go ahead and plug it in so that you don't get confused, but it's negative 40, 23 over 23, right? It's this portion right here, and this j is just to represent, actually, I don't really need to put the j right here because I already know that this is in the imaginary plane, and this is in the real plane, real part, okay? So technically, I'll have y and then 40 over 23, but, you know, I'll put the minus here too so that you don't get confused, okay? We're going to add the x and then the 4. And now we know all of this stuff, right? We know what our phi prime is that we want, and we know what our y was. We just need to find our x, which is the portion or the component that will take off this part right here. Okay, let's go ahead and plug everything in. So we're going to get tangent negative 18.19 is equal to negative 40, 23 plus x over 4. Multiply both sides by 4 plus 40, 23rds equals x. And we're going to see that x is equal to 0.424. Okay? So this part right here is 0.424, the amount of stuff, or like j, you know, or minus 0.424. Well, technically it's plus because, you know, you're removing it from this negative portion. See, the negatives and positives all get mixed and matched. Just pick it the way that you think is the best. I already know how to do this, so I have like a system in my head how I want to do it. But definitely pick what is best for you in terms of negative and positive. Okay, great. So we have this. This is not the answer, okay? Then the next step actually within step technically 3, right? We're still technically in step 3 and step 4, is to actually check that our answer makes sense, that 0.424 actually makes sense. And so we're going to check it right here. And how we're going to check it is that we're going to say that z total prime, right, is going to equal this is z total prime, right? Z total prime is going to equal 4 minus j 40 over 23 plus that portion we're going to take out, right? And we're going to see that it simplifies down to 4 minus j 1.347. And the idea here is that this complex number is actually going to get us the correct relationship that we're looking for by using tangent. And so we're going to see that it is negative 18.19 degrees, okay? And so that's how you know that this portion right here is correct, and that's how much we want to get rid of. And finally, we're going to move on to step 5, or, well, you know what I'm talking about, step 5, and that's actually to find the component. Now, when we see what we're adding, you can add a capacitor, you can add an inductor or something like that, but we want to find the simplest thing that we can add. And naturally, we've seen that inductors are typically within the frequency domain look like a positive J, and a capacitor typically looks like a negative J, right? As we can see here, this is just an observation, right? And we're going to use this observation, and this is an L. We're going to use this observation to our advantage so that we can get a simpler component, or only one component, rather than a configuration. I'm sure that there's a configuration where you can make the same, there's an infinite number of configurations, but we're trying to look for a component, only a single component. And so it would be natural just to use an inductor, okay? So the component that we're going to use right now is an inductor. And so we're going to go ahead and have our relationship here, and we know that we want 0.424 j 0.424 taken away, right? And that's going to equal to omega L. And the good thing is we already know what our omega is because it's right here, right? So we still do need that sinusoid even though we ignored it at the beginning. And we can now solve for L. So these j's cancel out, and we get that L is equal to 0.0848 henries. And so this is the component that we would be adding to increase our power factor such that our circuit is basically more efficient. And so this question mark is gone now, and we know that this question mark can be filled up with an inductor at the bare minimum that has henries of 0.0848. And that's it for this problem. So let's go ahead and do the next one. All right, guys, let's go ahead and solve this problem right here. So the first thing that we're going to do is find the impedances in the frequency domain. So I'm going to go ahead and do that. So our inductor right here is J times 10 times 1. And this guy right here for our capacitor is negative J 1/2. Now we're going to add these up because they're in series with one another. So ZH, not ZH, I don't want to call it henries, I want to call it the inductor. ZLR1 is equal to 2 plus J10, I believe. Yep. and then the capacitor is just 8 minus J1/2. And then they are in parallel with one another, so these configurations. So we're going to go ahead and make them in parallel by using our nice formula. And simplified, we get 5.048 plus J3.103. So the total resistance is 5 ohms, and the reactance basically is 3.103. All right, and then we're going to go ahead and solve. Let me move this down. We're going to solve for the magnitude of Z as well as the phase of the power factor, and then the power factor itself. And then we're going to use all of these things to find the power. Now remember, in this, this is the magnitude and this is the real part. Don't get confused with that, because I actually got confused with this problem and I had to redo it multiple times. But let's go ahead, and so now we know our power factor is 0.8518, and we need to find the actual power average, or the power, sorry. Oh yeah, it is the power average. And it's going to be 1/2 times 10 squared, because our cosine V max is 10. And we are going to multiply that by the power factor divided by the magnitude, which is approximately 7.19 watts. And that's the answer to part A. Now let's go ahead and draw the graph just so that we're ready for part B. And we see that we actually have a positive angle. So that means that our circuit currently is a little more inductive. And we're going to go ahead and draw the angle right here, and we're going to call it 31.58 degrees, because that's what we had found. It's a little bit more inductive, so I'm going to go ahead and draw it green, like that. All right. We know that this right here is our Y. Right. Now we can go ahead and move on. So B says add a component in series with the configuration such that the power, this is actually supposed to be the power factor. That's misleading. The power factor increases by 10%. So if the power factor increases by 10%, then that means that this value right here will get increased by 1.1, or 10%. So our new power factor is actually going to equal 0.8518 times 1.10, and that's equal to 0.937. Okay. Now we have the opportunity to find the new phi, because that's just equal to 0.937. And so our new phi is going to equal to cosine of 0.937, arc cosine, and that is about 20.43 degrees. The next thing that we're going to do is graph this, right? We're going to say that we want to go down, right? We want to go down to 20 degrees, 20.43 degrees, And the way that we're going to do that is we're actually going to subtract this x portion, right? Kind of like what we did before, except this time it's y, so y is positive, so we actually have to subtract the x, whereas down here y was negative, so we'd actually have to add the x to remove that portion. So we can go ahead and set up our tangent relation, which is the O, the opposite right here, and the A, the adjacent, which is just the real part of the impedance. So we're going to get tangent of the phi prime, the new phi, is equal to the y portion minus the x portion over the real part of z. Okay? And if we plug all of those things in, we're going to get tangent of the new phi, which is 20.43, is equal to 3.103, because we found that our portion of the impedance is 3.103 right here, right? And we are going to subtract that x, because that's what we want to find. We want to find this x and divide it by the real part of this impedance, right? Find the real, divided by the real component. And the real component is 5.048. And once again, it's just an algebra thing. I'm going to multiply both sides by the real component, subtract, etc., etc. So let's go ahead and do that. And because we have this negative sign here, we're going to divide by a negative. So actually, we could have just written it like this. And we get that x is about 1.22. Okay? Now, once again, this itself is not the answer. First of all, we're going to go ahead and plug this back into our equation and check it. We're going to check it by plugging it back into our original impedance, because we want to get the new impedance. So our original impedance was 5.048 plus J 3.103. And this time we're subtracting that 1.22 component so that we can get the Z total prime. Simplifying this down, we get 5.048 plus J 1.883. Okay, and now we can actually verify that our phi does indeed equal 20.43 degrees, because when we plug this in, 1.883 divided by 5.048 with the arc tangent, we will get 20.43. Now the last and final step is to actually find the component. This time it's negative, so we're going to want a capacitor for our single device. So determine component. And we found that the component was a capacitor. We're going to simply plug it in, negative J 1.22 is equal to, this negative J 1.22 is equal to 1 over J times 10 times C. And we know that this is just a negative J, so we can get rid of those. Multiply across and divide, or flip it. We get 0 is approximately 0.08196 farads. And that is all. So in this lesson, we went ahead and used what we know about power factors so that we can figure out components that can make the power factor bigger, or we can change how we want the power factor to be by adding a specific device. All right.